Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the fluid flow through branched pipes. So up to now, we have discussed many concepts regarding the fluid flow. So this is another one separate topic regarding the fluid flow through branched pipes. When multiple number of reservoirs are connected, we can see here multiple number of reservoirs means this is one reservoir, this is reservoir 1, or this is reservoir 2, and this is suppose reservoir 3, which is named by ABC. So when three or multiple number of reservoirs are connected in pipes with the help of pipes, so it may have one junction or more than one junction. Now see, when all these reservoirs are connected, so this is the connection from the reservoir 1 or A, and it is also connected to reservoir B or 2, and also it is connected to the reservoir 3 or which is named as C. So all these three reservoirs are connected with the pipe fittings. So when it is having one junction, this is the junction point of these three reservoirs, which is named as D point. Okay, so it may have one junction or it may have more junction. Then the system is called as branching of pipe system. Then we can say the system is called as branching of pipe system. Okay, when multiple number of reservoirs is connected with a number of junctions or a single junction, then it is called branching of pipes. Okay, now in this figure you can see that all these reservoirs are connected, or all these reservoirs are placed with different heads. You can see different labels are there, different label in the sense different heads only. Okay, now this reservoir is situated with a distance of ZA. So for how to find out this label or distance or head, so we need to consider a datum line for that or reference line for this. So the datum line is nothing but we can consider what is the ground level of that particular area. So we can select that ground level, or you can take a reference line for this from anywhere point. And the level of this or the head of this first reservoir can be mentioned by from here to here, that is ZA. This is ZA. Similarly, this is the tank 2, which is situated. What is the level, surface level of this water in the reservoir B? So that one also can be mentioned by ZB. Similarly, this is the third reservoir, and what is the level of this third reservoir? This is the level of this third reservoir of this here. So we can mark it as ZC. So these are the distance which is present or different levels of water surface. Okay, and that can be taken from a single point, that is reference line. Okay, and all this reservoir at this, you can see that connected at this number of pipes. So that is all these pipes are called branched pipe. So these things we have seen. Now in this, all these reservoirs and all these pipes, everything should be given. Like suppose this is the reservoir, height is given, what is the level of this reservoir is given. So from this reservoir, the fluid which is flowing through the pipe, so here also the length of the pipe should be given, and diameter of the pipe should be given, and what is the friction factor, of each pipe, not only the first one. Suppose this is first pipe, and this is second pipe, and this is the third pipe. All these three pipes are connected, and this is the junction point D point. So all these pipes are connected, and it is the junction point is D. So for all these pipes, this length, diameter, and friction factor should be given. So what you need to calculate here, this is applicable for first pipe, second pipe, and third pipe. All these pipes, L1, L2, L3, D1, D2, D3, F1, F2, F3. Now we can see what we need to calculate. We have to find out, actually from this concept, we need to find out what is the discharge. What is the discharge need to be identified, and what is the direction of flow direction. What is the direction of flow direction can be identified. each pipe. From each pipe, what is the direction of the flow, we can identify. To find out this discharge and flow direction, okay, we have to use some formulas which already you have discussed previously. We know that when the fluid is flowing through a pipe, what are the equations need to be solved and what are the concepts need to be considered, that already we have discussed in our previous lectures. So for example, when it is flowing through pipes, then we see when areas are given. Yeah, one more thing also, velocity I have not told here. So velocity also need to be considered here. Okay, for this pipe, velocity V1, L1, D1, HF1. HF1 is the head loss actually, and F is required to find out the head loss. So second pipe, similarly, velocity V2 and L2, D2, HF2. And similarly, for this pipe 3, this is V3, velocity V3, and the relative parameters L3, D3, HF3. Okay, now, so as the fluid is flowing through that, so first things we can solve, that is, though discharge need to be calculated, we need to consider the continuity equation. We need to consider the continuity equation, first one. So continuity equation is what? Now we know that what is the discharge is there. So there we can find out A1 V1 equal to A2 V2, and that is nothing but Q. So here we can say, now what is the fluid is flowing through this? Like suppose from here V1 is there. Let's suppose this is Q1. Let's suppose this is Q1. So the flow or the velocity, that the discharge which is coming out from here, and again if you can see this reservoir also situated somehow a little bit high. So the flow which is coming out from here, like see, from this pipe or from this reservoir, the fluid which will come here, it also will be go to, like, you know, move to this side. Again it will go to this side also. Okay, again from this reservoir also, there is a possibility that fluid will flow like in the downward directions, and it also come from here to here. That means the discharge from the tank 1 and the discharge from the tank 2, like tank 1 and tank 2, will be similar, will be equal to the discharge from the tank 3, like through this pipe to C point. That means what I can write here for the continuity equation, we know that A1 V1 equal to A2 V2. So this one we can write A1 V1 equal to A2 V2 equal to A3 V3. But here what we can write, the discharge we can write in other terms, like Q1 plus Q2 equal to Q3. Okay, this can be written here. Next, this is one equation. Second equation, we know that we can write one more equation. See, we can see here that there is a fluid flow through the pipes. So when there is a pipe flow is there, need to be considered the losses of energy. So the losses of energy can be in two types. One is major loss, another one is minor loss, what we have discussed. So here we know that minor losses can be negligible or can be neglected due to its very less. So here, but one more thing, we need to consider the major loss. So major loss used to happen due to the friction between the pipes surface and the fluid. So for that major loss, what I can write, that is Darcy-Weber's equation. Darcy-Weber's equation, that is nothing but the head loss. Also you can write the head loss due to this major loss, that is nothing but 4F LV square by 2 dg. So this is individual. This will be individual formula for, or individual value for each pipes, not a single one. Okay, next one. Yeah, next one is what? Next equation, the most important equation is next one, that is Bernoulli's equation. So Bernoulli's equation we have studied previously. So Bernoulli's equation also will be helpful or used for this particular flow when it is flowing through a branched pipe. Number of pipes is there. So Bernoulli's equation, we know that is P by rho g plus V square by 2g plus Z equal to constant. So that also you can write here. This is P by rho g plus V square by 2g plus Z equal to constant. So when multiple number of things are there, we can write P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z1 Z2 plus multiple number of equation we can write there. Okay. This is the concept. Now here we can see now all these reservoirs, what is there, you can see here. So from this reservoir, the water supposed to be come from this pipe to the next pipe. So here also the same thing is there. So let's consider all this line. The reservoirs are very large in contents. So the reservoirs are very large in contents, and the surface level of this water, you can see all the surface levels of this water. You can see it is open to the atmosphere. It is open to the atmosphere here. So that means here the P atmospheric is connected, or the atmospheric pressure is acting on that particular point. Okay, P atmospheric. So this is the labels. All these labels we can see all this in this container. Let's take that is the surface levels of the reservoirs at constant steady state condition. We can condition steady state condition is existing in that. That means there is no disturbance in that particular positions, you can say. So first let's see from the reservoir 1 or from the reservoir A, the flow takes place and it connected to the junction D. Then the D junctions from reservoir to B also and C also. Like sometimes you can see from D to B also moving, and D to C. And even though if the flow velocity is high, little bit pressure is high here, so it will be again come back to this direction. So what is the Q1 and Q2 is there, Q2, and this is Q3. So we can say this is Q1 plus Q2 equal to Q3. Okay. So now what I need to find out, each discharge or each discharge value from this each of the points, like from this container 1 to A to D, what is the value is coming, and container B to D and container D to C finally what is there. Now the flow, it came to A to B, one thing. Then from D to B also can be possible, and B to D also, and finally from B to here, from D to C. Okay, now arrow marks are given. We can see this is the velocity V1, velocity V2, velocity V3. Okay, now let's find out the what is the flows are there which is flowing through this each point, each junctions, like from A to D, then D to B, or D to C point. So for this I can write the Bernoulli's equation particular for these two sections. Okay, so let's consider this is one section and this is one section for each flow. So for this I can write here what is the flow from, I can write here, let flow from A to D. So what we can write here, the Bernoulli's equation will be applied for this from reservoir 1, like from A to D point. So I can write this is P A by rho G plus this is V square by 2G, that is VA square by 2G plus ZA. ZA is the total height from this diagram line. So ZA, this equal to, we can write again similarly PD, another one junction or another one section is there at the D point, we can write, and this is rho by G plus similarly BD square by 2G plus ZD. Now plus this is up to this only the Bernoulli's equation, but when you apply the Bernoulli's equation, we know that there is some losses also need to be considered, head loss need to be considered due to the friction factor. So that we can write at the end of this section. So always the head loss need to be considered at the right hand side of the last. That means once flow completed, then we can consider the head loss for that. So that is nothing but HF, head loss. From which point to which point, we can write from A point to D point. Anyway, if you add in this equation, then easily you can understand there is a section is considered the A point and another section is considered the D point. Okay, so at the end of this we have written the head loss. So now this equation can be written in another form, like we need to see this is the pressure head, this is pressure head, this is velocity head. So pressure head at this point, at this surface level, what we have considered here. So this surface is connected to the P atmospheric pressure. If you consider this is the surface level, or this is the initial point at this starting, so here the pressure which is there, that can be neglected, though it is connected, though you take this as a reference line, and though it is connected to the atmospheric pressure, so this pressure head can be neglected. This pressure head can be taken as a 0, as it is taken as a reference line, starting point. Now, similarly, though this container is very large, you can see this is a large container is there. So the water which is coming out from this container to this pipe is very small compared to the this container, you can say. So what is the, see here we can see some velocities of flow, like there is a fluid is flowing, so we can see some kind of velocity is there in the fluid. But at this level, at the surface level of this, or this section level, we cannot see any kind of disturbances in the fluid surfaces. That means the velocity also at this point need to be considered as negligible, or that can be taken as a 0. But remaining the Z point will be there as usual, because this is the height what we have taken from the datum line. So we can write here, this is ZA equal to, so come to the second one, like in the second D point. So D point, it is there, pressure is there, PD by rho g, that will be there at this ending of the pipe. So that we can write PD by rho g plus Vd squared by 2g. Yeah. So D point is situated at the junction of all these pipes. So mostly in the junction of the pipe, the velocity need to be considered as negligible, or can be sometimes taken as a 0 also, because we know that though the fluid is diverting in both of the sections, so at this junction position, okay, the velocity will be slightly reduced, or you can say it can be also considered as a negligible. So this part also can be neglected, or it can be taken as a 0. So what are the other things need to be considered? What is the height? What is the height from this datum line? So that is ZD. So that need to be considered, ZD. And what is the loss happened between this A to D? Head loss due to the fluid flow in this pipe A point to D point, that can be written, that can HF. In place of HF also I can write what is the values are there, 4F1 L1, and this is V1 square by 2 D1G. Okay, so this is the formula. Okay, now similarly, if we consider the flow from the B to D point, then that will be different. If you consider from D point to P point, that will be different. Okay, so both similarly in the same concept. Okay, again we will go to the B point, then we need to consider the surface of this B, and what is the fluid is flowing from that B point to D point, or D point to B point, we need to consider. So just I'll write the final one, like how I have written the fluid when it is flowing from A to D point. Similarly, let me write here the flow from D to B point. So D to B point means from here to here when it is moving. So similarly, we need to consider, or we can write here, this is ZD equal to, not equal to, ZD plus what is the pressure at this point, that is PD by rho g. So this equation also can be identified, or can be written in the same form what I have written here, and there we can find out what is the final one. So here also we can write, this is ZB, the height, the head of this surface level, ZB, plus this is what is the surface loss, or what is the head loss happened between this. Okay, this is flow from D to B. If it is there, then I can write in this way. But if you consider the fluid is flowing, suppose B to D point, then again that will be different. Okay, if you consider from B to D point, suppose I'm telling you, so that can be slightly different from B to D. If it is there, then the value will be slightly different. Like I can write here ZB equal to ZD plus I can write PD by rho G plus HF2. In this way we need to write, because this equation also similarly I'll get from by the like this only. So if I write this equation, Bernoulli's equation for this, what I'll write, PB by rho G plus VV square by 2G plus ZB. So here also similar concept, like the pressure surface level at this pressure will be considered the 0 as it is atmospheric pressure. So this surface level need to be considered as a reference line. So from starting we can take this is the pressure is 0 here, and next similarly the velocity here at this point, that is VV square by 2G, that also can be considered the 0 point or 0 value, because we have taken the the fluid which is flowing in this pipe, because the huge container of this, the size of the container is very large, so we cannot find out any kind of velocities flowing through this point. So that also can be considered 0. So by that way we can identify this is the flow from B to D, and this is flow from D to B. And final one we can write what is that, like a flow when the flow will be from D to C point. So when the flow will be from D to C point, what will be what I can write here. Now similarly I can write ZD will be there, plus again the same pressure, what is the pressure at this junction point, PD by rho G, plus what is the height. So this is equal to, we can write, this is height, we can write ZC, plus what is the loss is there, simple losses between this C to D to C point. So these are the things can be written, like these are the equations we can write for this. Now finally what is our target? Main target is we need to find out the discharge. Okay, so discharge can be written, we know that discharge can be written, I can write one more line here. So what is the final discharge is there, we can write QAD is equal to, we can write Q. Now for this particular point also we can write QAD equal to QDB plus QDC. So what I told you first initially, what is the Q1 plus Q2. So this Q1 plus Q2 is like means from this discharge plus this discharge supposed to be equal to here. Okay, but here in this case we can write like how is according to the flow directions. So I can write what is the discharge is coming from this Q point, that will be equal to this one Q2 plus Q3. So as per the flow directions we can write what I have written here, this is as per the flow direction of this one. That means QAD equal to, I can write here, this is QDB plus QDC. So if I write here, this is the formula, like Q1 Q equal to, we know that Q equal to that AV. So everywhere same thing, we can, if you write here pi by 4 d square everywhere. So let's write here pi by 4 here, this is d1 square and this is v1 here, and similarly I can write this is pi by 4, this is d2 square v2 plus again similar thing pi by 4, this is d3 square v3, and if I cancel all this pi by 4, so what I'll get here, this is equation. Finally we can write d1 square v1, then we can write d2 square v2 and plus d3 square v3. So this is the final equation of this. So from here we can find out what is the things required. Now remaining formulas, what is there, that also if any kind of unknowns are there or in the questions what is given, we can find out based on this formula also. Now here we see unknowns are, how many unknowns are there? Now, v1, v2, v3. If you consider these three equations, we can identify this equation also, you can find out this value. Now here unknowns are like v1, v2, v3, Apart from that also, this PD by rho g, because this is the junction point, the pressure head at the junction point, that is, see, PD by rho g mostly it will be there for all the points. PD by rho g, PD by rho g, PD by rho g, even here also PD by rho g. So everywhere PD by rho g is there because it's the junction point there. So by using this all this equation, so we can find out what are the unknowns are there, or what are the things asked in the questions. It can be identified, or it can be calculated. So this is all things regarding this flow through the branch pipe. I hope you understand this concept. So thing is that we need to consider, see, as I told you, first things, the continuity equation need to be considered, then the Darcy-Weber's equation due to the losses in the pipe, and finally the Bernoulli's equation. So all these equations also I have mentioned here, and what is the concepts are used here, that also I told you. So if still you are having any kind of query and doubt regarding this, you can give a comment on the comment box. Thank you all.